Hello class, we're going to start with section 1.1, a good place to start. We're going to go over lines and linear equations. Now, a lot of this stuff is going to be very, very familiar to you. It is pretty much the exact same stuff that you go over in Algebra 1 and Algebra 2 with your systems of equations. However, we are going to look at it through a lens of a higher order class, because this is linear algebra and this is a higher order class. So it might start off a little rough, it might start off a little unfamiliar, even though it is familiar material, and I did that on purpose because this is stuff that you've seen before, and this is this is an introduction to a higher level course. So we are going to look at something you are familiar with through the lens of higher order math, right? So there are going to be some things right off the bat that are probably unfamiliar to you. We're going to have an introduction into mathematical notation. We are going to start doing proofs in this course, although we're not going to start doing proofs right now. I think that's in the next section, 1.2. However, the mathematical notation, I'm going to start off right at the beginning, and it may be overwhelming at first, but you will get familiar with it as we continue to use it, okay? Now, I will walk you through the notation as much as possible. So, good thing is that this is on video now, and you can rewind and review things, as well as look at the write-ups that I have for you, okay? So let's go ahead and get started, okay? So let's talk about lines and linear equations, right? So I know a lot of you guys are used to linear equations in the form of y equals mx plus b, or maybe even in standard form as ax plus by equals c, right? When you're no longer just solving for y and the slope and the y-intercept, you put it in standard form, okay? So we're going to do the same sort of thing. We're going to have our own sort of construct as far as the way that we use variables go. So let's kind of go ahead and get started, okay? So a linear equation has the form a1x1 plus a2x2, so forth and so forth in this fashion until you get to an times xn equals b, okay? Now, remember, a linear equation is any equation where you do not have any powers. And that's basically it, right? There's no square roots here. There's no fractional exponents. There is no cubes or any powers of any kind, right? A linear equation means that your highest power is 1, right? It's an order 1 equation, or a first degree equation, I should say. So here, all of our a sub i's, we call this a subscript, our a sub i's are in the real numbers, okay? This means n, and this is the real number set. So all of our a sub i's are an element of R. Later on down the line, we will talk about when these things are complex values, okay? But for right now, we're going to restrict it only to the reals. Same with our variables. Our variables can be complex valued as well, but for right now, we're going to restrict them to the reals. We call these things constants, okay? Each of these a sub i's are constants. All of these x sub i's are variables, okay? And if you're not familiar with the x sub I notation, basically I is an integer value from 1 up until n, okay? A positive integer at that. And so our notation for positive integers is that I is in z plus such that I is less than or equal to n, okay? So if you don't remember your number sets, z is the integers. This little plus right here means I'm talking about the positive integers only, okay? So again, I wrote it in regular English, and then I wrote the mathematical notation in parentheses. Here, I wrote it in the math notation, and then I wrote the English term, right, for what I said in English. And I'll do this for the first chapter or so, and then as we get used to this, I'm going to stop writing the the translation, I guess you could say, because you should be used to it by then. We'll be seeing this sort of notation all over the place. A solution to a single linear equation is a set of values for x1, x2, up to xn that are fixed. Okay, so these are values of their corresponding variables, but are fixed in values. So this might be like 5, 7, -3, 2 8s, or something like that, right? So they're fixed values of the variables that we call an n-tuple, where if I were to multiply their values times their corresponding coefficients, that they'll come out to the value that I want it to be. Okay. The set of all solutions is called the solution set. So remember, sometimes there can be one solution, sometimes there can be many solutions. Right? We'll go over the cases in just a second. Let's do an example. Okay. Consider 2 times x1 plus 3 times x2 equals 5. Single equation. I have two variables. You may be more familiar with this as something like, I don't know, 2x plus 3y equals 5. So you have kind of two values here that change back and forth. We are not calling these x and y because we are not looking at these as an independent variable and a dependent variable, right? We're not looking at these as functions right now. I guess we kind of are, but we're not. We're looking at them as two variables that are working together to try to create 5, right? So, for instance, 1 and 1 works perfect, right? 2 plus 3 is 5, so if I have a 1 here, this works out well. But notice that since I have only one equation and two variables, one of these, I can really make any value I want, right? So let's say x2. Let's say I make this any value I want, okay? Then that means that I can adjust x1 so that when I add these together, they're 5, right? So 1 and 1 was easy, but I can find an infinite number of solutions. So for instance, let's say I chose 2, okay? If this is 2, then I got 6 here, right? 3 times 2 is 6. So now I can choose x1 to be whatever I want so that when I add this together, it gets 5. So in fact, -1/2 will give me a -1, so I got 6 plus -1 and get 5, right? And I can do that for anything. If I let this be, I don't know, 4, right, and I got 12, well, I need this to be something so that when I add it, I get out 5, right? So I need this to be 7, so I can make x1 be -7/2, right? So then when I add this together, I get 5. And I can do that forever and ever and ever, right? So 1, 1 is a solution. It's probably the easiest solution, right? And any solution to this is an 2-tuple, right? An n-tuple. But for 2 tuples, we don't call them 2 tuples. You've probably never heard that before. We just call them a coordinate pair, right? That's the general consensus for a solution in 2 space, in 2 variables. And any solution, the general solution to this will be S1, right? This x2, this variable in the second position that can change however I want it to be, this what we'll call a free variable. And then x1 can adjust according to whatever x2 is to make this work. So this one can be whatever it wants. And this one, I can manipulate this first one in this way so that this always works out. Okay, in fact, let's look at 1, 1. If this is 1 and x1 is 1, so what? I have 5/2 minus 3/2, 2/2, that'll be 1 also, right? So how do we put it into this form? How do we go from here to go to here? It's actually very simple. We just solve for the first variable, right? Solve for the leading variable. 5 minus 3x2, and then I divide by 2 will give me 5/2 minus 3/2, and I change x2 to be s1, right? I'm turning it into one of these things, okay? So the fixed variable is this last value, right? And then I'm adjusting the first variable based on whatever I choose for the second. Okay, so we'll talk about sort of the consensus on how to write these. It would be okay for you to write this as 5/2 minus 3/2 x2, and this as x2 as well, since it's x2 can be anything, right? It's your first variable that's going to depend on the second in this case, right? So we call s1 a free variable. Okay, so solving these into this general form is very, very straightforward, right? It's just you're probably not used to it. Consider this case now, right? We have one equation in one variable. This is very easy to solve for, right? I divide both sides by -5, and my solution is -2. And it's my only solution. Here I had infinite choices for an answer. Here I only have one. Okay, we call this a unique solution. So a collection of linear equations with the same set of variables is called a system of equations. So if I have a bunch of these equations where x1, x2, all the way up to xn are the same value for all of my equations, that's a system of equations. All right, so let's look at this in the general form. We have, let's see, a11 x1 plus a12 x2 all the way up to a1n xn equals b1. Now this is not 11. This is not 12. The next one would not be 13, 14. It does not work that way. The first one in all of these is telling me that I am in my first equation. The second value in the subscript is telling me the position of my coefficient. This is the coefficient in the first position in the first equation. This is the coefficient in the first equation, second position. This is the coefficient in the first equation, nth position, right? Or attached to that nth variable. And this is my first solution to the equation, I guess, right? Same thing here. This is not 21, 22. These are subscripts where this is telling me it's the second equation, first coefficient. Second equation, second coefficient. So forth down the line. And we do this for all of the equations that we have until I have m equations, right? This is my coefficient in the mth equation, first position, right? This is the second coefficient in the mth equation, right? So I'm trying not to say it backwards, but it makes more sense that way. We want to get used to it, thinking about it as the coefficient in the mth equation attached to the second variable, right? And so forth down the line. Now, this m, the number of equations I have, can be equal to n, the number of variables I have. In fact, when they're the same, when m and n are the same value, that's great. That's actually the best case scenario. There's a lot of interesting stuff that happens from there, but it's very possible that I have less equations than I do variables, or I can have more equations than I do variables. And there's interesting things that pop up when that happens as well, which we'll get into in more chapters, right, further down the line. So when n equals 2, the solution set to a single equation is going to be a line in R2, right? So that's what we were looking at over here. I had two variables and a single equation. And so this just created a line, right? This is really just another way of writing a line. This is just what all the points in this line look like, right? In fact, this is like if I said this was y and this was x, and then I solved for y, right? This looks like the y equals mx plus b form, okay? It's just that we're not using, again, y's and x's. It's x subscript because there's multiple variables here, okay? So, if I have one equation, two variables, my solution set is a single line. It's an infinite number of values, okay? And my solution is going to look like a point in R2, okay? In fact, it's the point of intersection if I have a system of equations in R2, right? So here I have two equations in two variables. If I had more equations, let's say I had 4 equations in two variables, I would have 4 lines here. And hopefully they all would intersect at the same spot. If they did not all intersect at the same spot, I would not have a solution. Okay, so if I have more than one equation, they all have to kind of go through the same point, because the point of intersection is what my solution looks like in R2. So this is 2 equations, okay, a system of equations in R2. This would have no solutions because there is no intersection, okay? And this would be 2 equations in R2 with infinite solutions. So this is more like this single equation in N2 where all points are equal. The 2 lines are laying on top of each other. There are infinite solutions. So this turns into the case where it is a single equation because they're both the same equation. Although they may look different. Maybe one is multiplied by 10 or something, or -1. And so that's what we would get, okay? So when n equals 3, the solution set to a single equation is a plane in R3, okay? So a plane. So think of a piece of paper that extends forever in its 2 directions. And the intersection of all planes is a solution set to a system of equations in R3. Now this is a little bit harder to quantify because this can be a plane itself, it can be a line, or it can be a point. All right. So in this case, each of these equations represent a plane. So my 3 equations in 3 variables has no solution if they have no points in common. They're all parallel to each other. They're basically the same plane, okay? So here my planes intersect in pairs, all right? So this plane and this plane form this line of intersection, okay? This plane and this plane form this line of intersection. And this plane form that line of intersection. None of them are all the same. There's no place where all 3 of these intersect together. Okay, so there are no solutions to this system either. Okay, remember, that solution needs to be where all 3 planes intersect, right? So this is just a little bit of the geometry of what it is that we're going to be looking at. Okay, here we have a solution. In fact, we have a unique solution. So all 3 of these planes, okay, meet up in this one point. Okay, that is the point of intersection here, right? Or we can have 3 planes that meet up at this line. Okay, so then this line represents our solution, and obviously a line has infinite number of points on it, right? That's what a line is. So this would be infinite solutions, a unique single solution, no solutions. Okay, so for 2 equations with 3 variables each, so again I have 2 equations, each of those are planes. Okay, so 2 planes, 2 of these planes, 2 of these planes, 2 of these planes, in whatever configuration, right? So these are the possibilities that we have for 2 equations and 3 variables. Again, that they're parallel, there's no solutions, or that the 2 planes intersect and then I have infinite solutions. So if I have 2 equations and 3 variables, there is no way for me to have a single unique solution, but I can have no solution or infinite solutions. Okay. A system with no solutions is what we call an inconsistent system, right? If there is a solution, then it's called consistent, right? And then we break that down into 2 categories. Is it a consistent system with one solution, a unique solution? Or is it a consistent system with infinite solutions? Those are our only cases, is that there's one solution or infinite. There is no way to have 2 solutions or 12 solutions. You have one unique solution or infinite many solutions. Again, none, infinite. Okay? None, none, a single unique or infinite. There's no way to have 3 solutions, right? It's one or infinite or none. That's all. Okay. A system with a unique solution where there's one is called an independent system. Okay. So if you're a consistent system with a unique solution, you're an independent system. If you are a consistent system with infinite solutions, you are called a dependent system, right? So these are our 3 system names: inconsistent, independent, dependent. Okay, independent and dependent, they are a subgroup of a consistent system, basically. Okay, so it tells you that you're consistent. So independent means one solution, infinite solutions, no solutions. All right. The first non-zero term in a row or in a equation, we should say, is called a leading variable. So an example, if I have this system here, okay, I have 3 leading variables. The first variable that shows up each time is the leading variable. So this is the leading variable for the first equation. This is the leading variable for the second equation. This is the leading variable in the third equation. Right? So x1, x3, and x4 are what we call leading variables. Okay? And that's because of where they show up in each equation. A system is what we call triangular, or in triangular form, if each new equation starts with the next variable after the equation before it. So this is not triangular because x2 is never a leading variable. So if this was your first leading variable, if this was the second leading variable, and then x3 was the next leading variable, we could call that triangular. Okay, technically not, but I'd be okay with it for right now. Okay, so the reason it would not be triangular though is for this reason. Okay, because we have more variables than we have equations in this system, so this actually can't be triangular. If we got rid of the x4's, then that happened, it would be triangular. So I'm saying ifs and this and all that kind of stuff. So let's just look at an example of a triangular equation. Okay, so again, you need to have the same number of variables as equations in order to have a triangular system, and each variable will be a leading variable once, right? So this last sentence here is the real definition for a triangular system. Okay, a triangular system will always have a unique solution. All right, so let's look at an example. This is triangular. 3 equations, 3 variables. Each variable is a leading variable at least once. Okay, not at least once, exactly once. Right? So solutions to systems in triangular form are found by back substitution, right? So we actually really like triangular systems because they're really easy to solve. So back substitution means that I start with the last variable and I solve for it, and then I just work my way up by substituting it into the next equation and so forth, right? So for this system, right, this is obviously the easiest thing to solve for. x3 is 2 over 9. Okay. If I substitute that into this and I solve for x2, I'm going to get negative 8 minus x3, right? That's going to move over, so that's going to be minus 2/9. And then to finish solving for x2, I divide everything by 5, right? So that looks like this. Minus x3 divide everything by 5, right? Substitute this x3 in, okay? And then I can finish solving this for what it actually is. I can do common denominators and all that fun stuff, right? And you can do this on your own and check, but you should get out 74 fifths on the negative side, okay? Now I know what x3 is, I know what x2 is. I can take these two values and I can solve for x1 by doing the same thing. I can add 4x3 to both sides, subtract 3x2 on both sides, divide everything by half, okay? And then substitute in my known variables, okay, to finish getting my solution. Now, I will say this, you should definitely be taking notes as I am going through these, if I haven't said that already. I'll try to go slow so that you guys can copy things as I write it, or maybe you want to stop and pause or go through a video a second time, whatever your preference is. But you should 100% have your own book of lecture notes. Even though I have these videos and I have the write-ups for you, writing it out yourself, doing some math and some scratch work on the side is definitely going to be helpful. So not only that, but if you notice, in order to go through this, I got to go back and forth between screens if I want to go back and show you something over here. So if you have it in your notes, it's a little bit easier for you to follow. Okay, so I highly suggest, especially since everything is online right now, that you take notes as I go through these videos. Okay, so my x1 value, if you have not calculated that already on your own, should be 307 over 90. And so this gives us our first system that we solved, where we now have our 3-tuple solution, right? My solution is x1, x2, and x3, right? So in order. There you go, right? Now, I don't think I should have to say this, but if you want to check whether or not this is actually the right solution, you take these values and you plug them back in, right? If I plug this in here, I should get out 1. If I plug this in for these two, I should get out -8. And if I plug in 2/9 to x3, multiply by 9, I should get out 2. This means you can check your answer on everything in this class, okay? Just like in regular algebra. It is a good habit to have to check your work, because you can know if you're wrong, you can fix your mistake. Okay, so get in the habit of checking your work, especially since I know the majority of you are really dependent on your calculators. It's really easy to just plug this stuff into your calculator, see if it comes out to 1 or not, right? And -8 and 2. Remember, the solution has to work for everything. It can't just work for one equation, it has to work for all. Okay, so this solution is a unique solution since it is the only solution we get, right? There's no free variables here. There's nothing telling us we have an infinite number of solutions, okay? Therefore, since there is a unique system or a unique solution, this system is an independent, consistent system. So every linear system in triangular form is in what we call echelon form. Okay, this is a very important form. We will go through the different echelon forms, but we always want our system to reduce down to an echelon form. It makes it very easy to finish solving when it's in this form, obviously. A matrix is an echelon form if it has a stair-step pattern, right? So notice that it looks like a set of stairs, kind of upside down, right? If we go backwards, even this, which was not triangular, this is still in echelon form because I have my leading variable, and then when I come to my next equation, I move in quite a bit before I meet my next leading variable. Okay. Do we have something? All right. I haven't had an example of something not in echelon form yet. So far everything's been in echelon form, which is good. Okay. Okay. So a free variable, again, is a variable that never appears as a leading variable, right? So we had an example of one, but we never quantified exactly what it was. So it's whenever we have a free variable that does not show as a leading variable in echelon form. So again, let's go back quite a bit here. When I said x1, x3, and x4 were leading variables, there was only one that was not a leading variable. That would be a free variable. So if you're in echelon form and one of your variables is not a free variable, or sorry, if one of your variables is not a leading variable, it will be a free variable. It has to be in echelon form though. If you are not in echelon form, you cannot determine whether or not you have free variables. Well, you cannot determine which variables are free variables, okay, if you have them at all. Right? It has to be in echelon form, and then you can start to determine if you have a free variable or not. Okay, it has to be in echelon form. So a system can have more than one free variable as well. So far we've only seen an example where we have one, but we can have more than one. So let's take this example. Okay, so you would think you had a free variable here, but actually we have a false statement. So we haven't seen an example yet of an inconsistent system. This is an example of an inconsistent system. I have a false equality here. There's no way that 0 is the same thing as 3. That's not true. So if I ever reduce my system down and I have a false value here, I don't have to do anything else. My system is inconsistent. Okay, so there is no solution. Now here, this is the same example we had from the beginning. I have free variable, leading variable, leading variable, leading variable. This is the free variable. Okay, it's in echelon form. x2 is not a leading variable for any of the equations. Therefore, x2 is a leading variable, is a free variable. Okay. Now you've seen this a couple times. These three dots. This means therefore. We use it a lot when we're doing proofs. We also use it a lot in just generic sort of explorations, derivations, things like that. Okay, so it's a very mathematical term. It's basically math notation is just shorthand. Okay, it's a math shorthand. That's the easiest way to think of it. It's a lot of symbols to represent bigger ideas. This means therefore. You're going to see this a lot. I use the therefore symbol all the time. So every time you see these three dots, it means therefore. Again, I talk through what these things are, right? So you'll get used to their meaning fairly quickly. Okay. So since x2 is not a leading variable and I'm in echelon form, it's a free variable. Okay. So if I want to, I can go back and I can still solve, right? A free variable does not mean that there's no solution. A free variable means, that was a dramatic pause, it means you have infinite solutions. x2 can be anything I want. Okay. So that doesn't mean I can't find solutions. This means I can't find solutions. Here I can still find solutions. I can find infinite solutions. So what I want to do is like I did in the first example, where, sorry for going all the way back, you guys, but where I call one of my variables free, and then the other variables I solve in terms of that free variable. Okay, because now everything depends on it, right? Do you remember what we said? If I have infinite solutions, okay, if I'm a consistent system with infinite solutions, I am a dependent system because everything depends on what the value of that free variable is. This is my free variable, so x3 depends on what I choose for x4. For x2. x1 is going to depend on what I choose for x2. So x4 I can solve for. x4 will always be 7/8. x3, so 3, move this over, right? Plus 2 times 7/8. Oh, that should be a plus, you guys. Apologies. I'm sure the math is fine though. Okay, that would be 1/4. And x2 will be s1, which is a free variable. And x1 will now depend on s1. And I just plug in all this stuff, right? So I have 1, I minus the x4 times x3, which is 1/4. Okay, I'm going to minus 2 times my free variable s1, and I will minus x4, which is the 7/8, which gives me this value. So now x1 depends on this x2 value, right? So therefore, any solution of the form -2/3 s1 plus 3/8, second value being a free variable, this one has to be 1/4 and this one has to be 7/8, will satisfy this system. Okay, so again, apologies for this. I will change this value in the write-up. So I try to catch my errors as much as possible, but I mean, obviously there's a lot of content that I have to write up and type up, so errors do slip out. But I will fix this in the write-up that goes along with this video. I just did a quick calculation, and this is actually not 1/4, so I did write this up wrong. So I'll make sure to fix this value. It should be 19/20. So I'll fix the rest of these values in the write-up. But really, this example was just for posterity, is just to show you how these things work, right? So I'll go ahead and fix this. So when you read through the write-up of this, it'll have the right values, but the important thing that I want you to take out of this example is how you write the solution for a dependent system. All right. So therefore, there is no unique solution, right? Because it's a dependent system. That's actually what we're going to conclude with. But since there's a free variable, there's no unique solution. Therefore, this system has infinite solutions. Therefore, this system is a dependent consistent system. So you see what we're doing here? We're kind of coming to a conclusion by logically taking it step by step. Okay. So one more time. Therefore, any solution to this system has this form, which we'll fix in the write-up. Okay. Therefore, there's no unique solution, because there's a free variable, right? So since there's no unique solution, that means that this has to have infinite solutions. And since it has infinite solutions, we can classify it as a dependent consistent system. Okay. So again, using the placeholder for x2 as s1 is optional. Okay. The book does this. This is what the book does. So the book will have its dependent systems written like this. I will start to, I don't know if I do it in the next section or after chapter 1, but I prefer to just use the free variable. Okay, so for me, what I'm going to write is I'm going to write, instead of s1s, where this is my first variable, I'm going to write it as x2. I'm just going to keep x2 everywhere. That's kind of the way that I was taught. This textbook will introduce a new variable for this variable, for your free variables. Okay, so I don't want you to get too confused. I know it's already kind of possibly confusing with all these new terms and notations and everything like that. But I will be not using the S1, S2, S3 format. I will be just using those variable names that are already given to the variables. I think it's simpler that way. Again, that's how I was taught. So that's what I'm going to go with. So that's going to be a little bit different from the textbook. So I'm just letting you know that now. Okay. So I will write my solutions like this in these videos and in the write-ups that I have for us. All right. So again, all of these values are the same. Okay. It's just that instead of S1, I'm using the actual variable value That's the free variable, which is x2. Okay, so that's what I'm going to be doing for this class, right? That's really the only difference that I'm using against the book. Okay. Hope this was enjoyable. Hope you learned something. Again, if not, just go back and rewatch it. Okay. Thank you.